RHS Pre-calculus presents graphing polar coordinates and converting rectangular to polar form. Today we're going to cover how to graph polar coordinates and how to convert rectangular coordinates to polar form. We have used a rectangular coordinate system in the past. Now consider a different system called the polar coordinate system.
Polar coordinates is just another system for graphing points, like the rectangular system. But instead of graphing by x and y, you use r and theta. With rectangular coordinates, you move left or right x units, then upward down y units. For polar coordinates, you turn from standard position, theta degrees, and then move outward r units. Each of these circles are 1 unit away from the center. This is the polar axis. At the center, what you originally called the origin is the pole. You go theta degrees in your direction, and you measure out how many units based on your r, 1, 2, 3, r, and theta, to your terminal side.
If r is negative, however, you have to move backwards from the actual direction you're moving. So if you take the coordinate -4, 30 degrees, we rotate our imaginary line 30 degrees clockwise from standard position. Then we move backwards 4 units. That's how you represent negative r values.
To convert rectangular coordinates to polar coordinates, you first graph the rectangular point like this and create a triangle. Now, using simple trigonometry, we can find theta. The tangent of theta is equal to y over x, so the arctangent of y over x is theta. That gives us the angle of the polar coordinate, so now all we need to do is find r. To find r, we apply the Pythagorean theorem. This gives us r squared equals x squared plus y squared. Then solve for r.
For example, take a look at this point, 3, 4. To convert it, we draw a triangle like so. Notice how the lengths of the sides of the triangle are linked to the coordinate. The x in the point is the x value of the triangle, and same goes for y. Now we know that the tangent of theta is y over x, so the arctangent of 4 over 3 equals theta. So we use our calculators to approximate the angle to 53.13 degrees, and that gives us half of our polar coordinate. Now to find r, we use the Pythagorean theorem. This gives us r squared equals 3 squared plus 4 squared. Simple algebra to solve for r tells us that r equals 5. So the polar equivalent to 4, 3 is 5, 53.13 degrees.
To convert the other way, as in polar to rectangular points, you do a simple procedure. You plot the point in polar form as before and draw the triangle. This time we know r and theta and are solving for x and y. To find x, use the equation cosine of theta equals x over r. Then you just solve for x. To find y, you use the equation sine of theta equals y over r. Then you have both elements of the point and plug them into the coordinate.
For example, let's convert the point 3, 135 degrees. Plot the point on the polar coordinate plane like so. Then draw the triangle. Notice how r and theta are labeled, and x and y are the unknown values. To find x, we use the equation cosine of 135 equals x over 3. The cosine of 135 is negative root 2 over 2. Then we multiply both sides by 3, giving us r, or to find x. To find y, we use the equation sine of 135 is y over 3. The sine of 135 is root 2 over 2. Multiply both sides by 3 and find y. So then we have both parts of the rectangular point, and we can make the coordinate x, y. Polar coordinates are useful because they make representing and graphing shapes, like circles, much easier. A real-life example for the use of polar coordinates is mathematically representing the orbit of a planet around the sun. This is possible to do with a rectangular equation as well, but is much simpler to do in the polar system.